Welcome to the third video in SLO 11. In this video, we'll be looking at a special reaction of anilines, compounds like this, amines bonded to aromatic rings, that's called the Sandmeyer reaction. So one example of a Sandmeyer reaction is shown here, where we could take some kind of an aniline. In this case, this would be 4-chloroaniline, and react this in two different stages. First with sodium nitrite and sulfuric acid, and then with copper bromide in this particular example, and we would make this kind of bromo or aromatic bromide, right? And we can see that the chlorine shows us something about regiochemistry. So it looks like we're directly substituting an NH2 group for a Br, right? So we have a para relationship between the NH2 and the chlorine, and then a para relationship between the bromine and the chlorine, and that's a hallmark of the Sandmeyer reaction. So we also notice that the halogen in this copper salt ends up in the product, right? That's important. So we can say something like the Sandmeyer reaction is a substitution of NH2 for another group. That group will typically be a halogen, but it doesn't have to be. We'll see a couple of examples where it's a non-halogen group. So what I'd like for us to do next is to think about what forms from the first step. So we'll think about kind of like a mechanism. We'll do a proper mechanism in a minute, but just the structure of the reactive intermediate that forms after the first step. So I'll just rewrite the reagents, sodium nitrite and sulfuric acid. And what forms is an interesting structure where we still have the nitrogen from our aniline, but not the hydrogens. We have two nitrogens bonded to each other and the aromatic ring, and if I look at this carefully, this nitrogen is going to have a lone pair, and this nitrogen will be positively charged. So this kind of a compound is called a diazonium ion. Which sounds like, I don't know, a little bit strange, but it makes sense in this in that we know di means two, and azo or ase means nitrogen. So this is a two nitrogen species. The IUM tells us it's positively charged. So most of this word makes sense to us. And in particular, the functional group that's new to us, and also I think pretty interesting, is what's called the Diazo Group. So a diazonium ion contains a Diazo group. So this group then decomposes in the presence of copper salts typically, and some kind of a halogen like Br. So like we have a two-step process, the Sandmeyer reaction proceeds through a diazonium ion, and then the diazonium ion gets turned into the halogen or whatever the group is that we're adding to the ring. So the other thing that I want to point out is that we lose N2. Right, so we're losing N2 here. Sorry, that shouldn't be a negative charge, it's like minus, so one of the other byproducts is N2 as a gas. And that tells us that this diazo group is acting as a leaving group somehow. In fact, the diazo group is probably the best leaving group that we know of. Because if we look at what we're making, N2, super stable molecule, 80% of our atmosphere, right? Much more stable than, say, like a water molecule coming out. So we have the same idea that we've got this positive charge that's highly unstabilized, just like protonating an alcohol, for instance. And then by virtue of using that group as a leaving group, we're making it neutral into a very thermodynamically stable structure. So the Sandmeyer reaction has a kind of a lot of features here. This formation of a diazonium ion, using N2 as a leaving group, and then being able to actually substitute an NH2 group at the end of the day for a halogen or some other group, which is actually quite useful. This reaction gets run on an enormous scale every day, because most of the compounds that look like this, that have halogens on the aromatic rings, a lot of them are made via this Sandmeyer reaction. So in the next section of the video, we'll actually look at the mechanism for this first step, the formation of the diazonium ion. So the process of making a diazonium ion is called diazodization. So this is basically the process of taking an aniline of some kind and turning it into a diazonium ion. And it turns out the way this is going to start is by interacting the nitrite anion. So this would have come from NaNO2 and sulfuric acid. So I've drawn the structure because we're going to use one of the protons and the rest of the compound kind of acts as a spectator. There are reasons why we use sulfuric acid and not, say, HCl, which we'll talk about a little bit later in the video, but they're kind of details. I wouldn't worry over much about them. So how these two compounds interact, the only thing I see that's reasonable is acid-base chemistry. We've got an extremely strong acid, and we've got an oxygen that's negatively charged, so this should be at least somewhat basic. Probably less basic than hydroxide, but somewhat basic. So we can propose a proton transfer where we protonate the nitrite anion. So that will yield a compound that has kind of a fun molecular formula. This is nitrous acid, or HONO, and the bisulfate anion. So this is the conjugate base of sulfuric acid. So one of the things that you might not appreciate initially is that, like, the way we run these reactions is a lot of sulfuric acid. It's almost like a solvent for the reaction, which is kind of disgusting. And that means that, like, multiple protonations can happen. It's not like this is catalytic in acid, right? So we've got a lot of sulfuric acid we can use. And that also tells me something else, that this nitrous acid could get protonated again. Because right now I don't see any good interactions between the aniline and the nitrous acid, right? I don't see, like, an electrophilic site in here that I feel very good about. So we can protonate this compound again using another molecule of sulfuric acid. But if we look at these two oxygens, one of them is more basic than the other. We know that if we could donate this lone pair to this oxygen by resonance, which should work, this oxygen is going to be partially negative and this one's going to be partially positive. So just like protonating an amide or a carboxylic acid or something like that, it's like the double bonded oxygen that's more basic than the single bonded one. So we'll show that with the lone pair here. So we've got another proton transfer to nitrous acid, and that gives us a species that looks like that, and then another molecule of the conjugate base of sulfuric acid. Okay, so now I see what looks a bit like a protonated carbonyl. So the positive charge on this oxygen makes this nitrogen extremely electrophilic. Right? I can't form another bond to this oxygen. I'll go over the octet rule. But if I use a nucleophile toward this nitrogen, I can break this NO double bond and put electrons onto the positively charged oxygen. So this oxygen is like creating electrophilicity for its neighbors. And now the aniline can get involved. So I'm going to draw the aniline out with my NH bonds shown explicitly. And the lone pair, because I'm going to use those features. Oh, there's a little small, make it bigger. There we go. And like we've been talking about, this lone pair can be like a nucleophile to make an NN bond, which we know we need to do, right? If we look at the structure of the diazonium salt, we've got like 3 NN bonds that we need to account for. So we need to start by making the first one, and then we'll find ways to make the next 2. So this is the crucial first NN bond that we're forming. So we'll start working back to the left now. And I'm going to abbreviate this benzene ring as pH to save a little bit of space. Okay, so this is a pretty strange looking structure, right? That's okay. We're just following what we understand about structure and reactivity here, right? We saw acid-base chemistry. We're looking for a good place to we're making a better electrophile so that we can use our aniline as a nucleophile. That would make sense given the fact that we're making an NN bond. So we get to an intermediate that looks like this, right? And at this point, it looks like I need to start introducing more nitrogen-nitrogen bonds. So that means I need to start, 1, removing the hydrogens from this nitrogen to make space for the new bonds. And I need to start losing these OH groups to make space for the new bond. So if I think about it, I need to like lose an H from this end and an OH from this end, which sounds like a loss of water. Or an elimination. And the way that that's going to happen, or the one way we could explain this happening, is first a proton transfer from this nitrogen, so this H, will go to the oxygen. So it's like an intramolecular proton transfer. We've seen these before with tetrahedral intermediates. It's a stretch, but if you look at this nitrogen, it's a little bit like a tetrahedral intermediate. We made this nitrogen kind of tetrahedral by virtue of adding to the nitrogen and breaking a double bond. So we're really doing an analogous kind of step here to what you've seen with the formation of imines or acetals or our snack reactions, all that stuff. So one of our OHs will stay the same, the other will end up as a protonated oxygen, so positive charge like that. I'll get a nitrogen lone pair. The other nitrogen lone pairs have always been there. Okay, and then one lone pair on oxygen. Lots of lone pairs. So I'm part of the way there now. I have what's now an excellent leaving group. Do that in green. And I need to find some way to kick it out, to eliminate it. But I have a lone pair on nitrogen that I can use to do that. All right, so I'm going to use a relatively high electron density on nitrogen to shove off a water molecule. And that will give us an NN double bond. It'll make this nitrogen positive. And so now I'm going to look at what I have to accomplish, and it looks to me like I need to do the same thing, right? I'm going to lose this OH group. I need to lose this H. I need to eliminate again to make another nitrogen-nitrogen pi bond. So this would be the third or the triple bond of nitrogen. And so I'll do it the same way. I'm going to first proton transfer. This is going to look a little wonky, right? This is probably assisted by sulfuric acid, but I'm not going to show it that way. So think about the proton coming off, floating around, eventually sticking to the oxygen. Obviously, this oxygen cannot reach this hydrogen directly. So this is just bookkeeping. That's going to put a lone pair on my kind of internal nitrogen. So I have a structure that looks like this now. And I'm going to do the same kind of a thing. I've got another good leaving group. And I've got electron density on a nitrogen I can use to kick out water. So another elimination. And if I follow my arrows, I'm now going to have a nitrogen-nitrogen triple bond. I'll have a nitrogen at the end with a lone pair, and the nitrogen in the middle, I guess, will be positively charged. So I lost another molecule of water. I have a species that looks like this, that is the Diazonium Ion, right? I'll just redraw it in a way that looks more familiar. Remember that pH is a benzene ring with a substituent, and the substituent in this case will be a Diazo Group. Right, so we made our diazonium salt here. So just to reiterate, what we're doing is essentially generating a better electrophile at this nitrogen center using acid. Because we have so much acid, one, this is not catalytic. You can see we're not getting acids back. And we're actually going to protonate our nitrite twice. And that's to get this nitrogen to be electrophilic enough that the aniline can actually act like a nucleophile. And that gets us started to make our nitrogen-nitrogen bonds. So in the next section of this video, we'll turn our attention to the second step of the Sandmeyer reaction, where we're actually consuming the Diazo group and replacing it with other incoming groups like halogens. Let's take a quick tour of what we can replace the Diazo group with, or the N2 group, with in a Sandmeyer reaction. So typically these reactions will involve copper, and the anion that's associated to the copper 1, right, it's a copper 1 salt, will end up attached to the aromatic carbon where the N2 was. So remember, this N2 is effectively acting like a leaving group here. And so what we've already seen we can do is to react this with copper bromide. So CuBr, and that will replace the N2 group with a Br atom. We could also do this with a chlorine to make an aryl chloride. So that would be CuCl. So a very similar pattern. We're just changing the halogen. And that will give us a similar product. But instead of a bromine, we'll have a chlorine. So we could also do iodine to make an aryl iodide, like so. And in this case, you could either use copper iodide, so CuI, or it turns out with iodine, it's kind of special. You can use just iodide sources like sodium iodide or potassium iodide. Those both work. So I'm going to write CuI or NaI, your choice, whatever you've got laying around. But that's a special case, right? So for the chlorine or the bromine, you must have the copper for this reaction to work properly. So a couple of other reactions I think are kind of interesting. One is you can actually add nitrile groups. So you can use copper 1 cyanide, so CuCN, so that's the copper 1, and then a cyanide ion, which is negatively charged. And so you'll have a nitrile, like that. And then finally, you can also take these compounds and you can effectively hydrolyze them. So you can use water and acid, so like more sulfuric acid, for instance, and that will give you an alcohol group, or a phenol. Right, so phenyl and phenol are not the same thing. Okay, so 5 different reactions of this diazo group. There are many more, right? These diazonium ions are very versatile synthetic intermediates that can be converted into lots of different structures. You can fluorinate them. You can make aryl fluorides with an F this way, although the reaction's a little different because copper fluoride is not a particularly stable compound. So use different kinds of species with some other additives and stuff. I'm not going to get into those details, but just so you know, if for whatever reason later in life you're like, man, I need to make this aryl fluoride, Sandmeyer reaction is a good way to do it. So this is kind of complementary to electrophilic aromatic substitution in the sense that you can replace these NH2 groups with these halogens, and you don't necessarily have to worry about directing effects in the same way that you would have had to earlier, right? So it's like if you need to add a bromine meta to some other group, well, maybe if you have an NH2 meta to that group, you can just do the substitution directly. So we don't have ortho, para, or meta directors for the Sandmeyer reaction, right? Once we have that NH2 group, we can directly replace it with, well, you can see here, kind of your options. The other thing I want to point out is that the mechanisms for these reactions are not well understood, and they really actually depend quite a bit on the substituents that are already on the ring. So for instance, if we were looking at this conversion of a diazonium ion to our aryl chloride, if we had a nitro group para to where the chlorine is going, the mechanism might be one thing, and if we had like a methoxy group here, for instance, the mechanism might be different, right? So kind of an open-ended question about what exact mechanism is operating for a given Sandmeyer reaction. Because that's true, we're not going to discuss the mechanism for the second step here. One of the leading hypotheses, and it's very common, is it involves radicals, and that's part of what the copper is doing, is it allows us to access those kinds of radicals. So really think about this as a useful synthetic tool to introduce these halogen groups, and then also to do some cool chemistry where you're making aryl nitriles, which is great, because we can use this as a handle for Grignard reaction additions or reductions to amines, whatever you want to do. And then also it's a good way to make phenols. It's difficult to make these compounds in other ways in a controlled and high-yielding fashion. So like I said, Sandmeyer reaction here, it's more about like what you can make than understanding a mechanism, right? Okay, so that covers our basis for the Sandmeyer reaction. At this point, you should be set for most of the content in SLO 11.